Today's lab is designed to hopefully verify the law of conservation of momentum in 2 dimensions. We did one already that verified, in some cases, the law of conservation of momentum in 1 dimension. Today we want to do it in 2 dimensions. So it's going to start off this way. You're going to take 2 objects. They're going to actually be 2 baseballs. 2 baseballs that theoretically should be the same mass, but in all likelihood won't be exactly the same mass. So you're going to have to measure the mass of both baseballs, mass 1 and mass 2, in kilograms. Make sure you keep the baseballs straight. Now, I've done some labeling on these baseballs, some of them in red and some of them in blue, and that's on purpose. I've done some of them in red and some of them on blue because in your video, it's going to be a little bit easier to distinguish which one's which if you can see colors, right? So pay attention to which one's which. I think it's the blues that are labeled number 1. Okay, pay attention to that so that when you're watching a video, if you can't see the number that's printed on the ball, you can at least know that, oh yeah, blue was number 1 and red was number 2. All right? Make sure you label the correct masses there as well. Now, essentially what's going to happen in today's activity is you're going to roll 2 baseballs towards each other so that they collide in a 2-dimensional interaction. Generally, it will be some kind of glancing collision like this. You could try doing it something like this. It doesn't really matter. Doesn't really matter. That's not going to be helpful to do it like this because you're not likely going to be able to do a 90-degree collision very easily. So in all likelihood, it's not going to be exactly 90 degrees even if you try. Just make sure they collide, and make sure when they collide, they bounce off of each other. They bounce apart from each other. Now, I told you a few minutes ago, you're going to analyze this using a software program called Tracker on a PC. That software program knows how much time has gone by in each interval of time because it knows the frame rate of your phone. What it doesn't know is the distance. So what you have to do when you're videoing this from preferably high above so you have a nice big field of view, when you're videoing this with your phone completely at rest, not just being held up here with your hand on your tiptoes, trying to keep your phone steady with your hand, find some way of keeping the phone at rest. Okay, what you want to do is put a meter stick in here. You have to tell the computer what a meter is. The computer has to have some kind of frame of reference of what a meter is. So you got to put a meter somewhere in that field of view. Make sure that the meter stick is not hit by the balls before or after the collision. So make sure it's out of the way. It doesn't matter where it is. Okay, if you set this up completely differently and the meter stick is vertical over here, it doesn't make any difference as long as you can see it, or at least see a good chunk of it in your field of view. Yeah, go ahead. It can be diagonal, it doesn't matter. Okay, what it can't be is a 3rd dimension. So you can't stick it straight up, obviously, right? But as long as it's on the XY plane, it doesn't matter what direction it is. Okay, set it up in a way so that the baseballs don't hit it before or after the collision. Why do we not want the baseballs to hit it before or after the collision? It'll affect the baseball, yeah. There's a term, though, that we talked about there. It starts with an I. Or it's not I. Isolated. It's not an isolated system if it hits the meter stick, right? There's an external force acting. There's going to be external forces acting anyways, but we want to minimize that as much as possible, make it as close to isolated as we can. So there's what it's going to look like, basically. Once you have your video, you're going to email that video or upload it to your Google Drive or somehow get it to a computer, to a laptop. And then you're going to open a software program called Tracker in order to analyze this. This is what the Tracker program is going to look like. The next bunch of slides are going to be identical to the slides that appear in your little lab manual that each group is going to have. So you don't need to copy this down now. As long as it makes sense, you're going to be able to go back and refer to this slide presentation to the letter. All right, so how do you do it? Once you got your video on your computer, okay, wherever it is on your computer, Google Drive, wherever it is on your computer, you're going to want to open that video from within the Tracker software program. So you're going to literally click this little button up here that says open the file that you want to analyze. And then once you have the video open, you can see that I have it open there. You want to click this little, I don't know, is that a fuchsia? purple, pinkish, whatever color that is. So it's a little XY coordinate system. You got to click on an axis button because you have to tell the computer what to measure from. It's a frame of reference. Okay, right now, if I measure my position, I could say that I'm 2 meters from the front wall, or I could say that I'm 6 meters from the back wall. It doesn't matter where I measure it from, but I have to measure it from somewhere. Okay, that frame of reference is going to tell the computer where to measure it from. That make sense? Where you put it doesn't matter, but it's got to be somewhere, and everything has got to be measured from the same frame of reference. Now, you have to create what we call the calibration stick, which is literally telling the computer what a meter is. So you're going to click up here on the tracks button. Again, it's outlined right here. Then new within the submenu, and then within the submenu, calibration tools, then calibration stick. Click on that. That's going to create a calibration stick that's in blue here. You're going to drag that around until you can superimpose it over top of your meter stick. Now, if you're like me here, I messed up when I took this video. I didn't get the entire meter stick in the video. So what did I do? I changed the length of the calibration stick, and although it's difficult to see in this video, I changed the number to 30 centimeters. So instead of having a 1 meter calibration stick, I measured it 30 centimeters on my meter stick and just changed it to 30. Make sense? So it's easiest to have the entire meter in there and then just to label it as 100 centimeters. But if you mess up like I did, it's not the end of the world. You don't have to go back and do it again. You can just calibrate it as 30 centimeters instead. All right? So now I have my frame of reference, I have my calibration stick, I'm pretty much ready to go now to collect data. So how exactly am I going to collect data? Well, I have to create in this software program 2 masses. Why? Because I have 2 masses in the video and I have to trace those 2 masses. So I'm going to create a point mass and I'm going to create another point mass. So literally just go through this process twice. Create a point mass, create another point mass. One of them is going to be called A, one of them is going to be called B. The next thing you're going to do is literally at the bottom here, scroll along the bottom here until the balls have left whoever is throwing them. Baseballs have left their hands. Why do we want to do that? Well, we don't want to analyze when the ball is still in your hand because then we don't have an isolated system. So we want to analyze it after the baseballs have left the hand. So scroll on the bottom just to completely ignore those data points that occur before the ball has left the hand. So now we're ready to start. Hey, got it? These baseballs, or these are actually road hockey balls, but you're going to use baseballs, have left the hand. We're ready to start analyzing. Let's say this, by the way, was object number 1. This was object number 2. Now what you got to do is click on mass A. Click on mass A. When you've clicked on mass A, right up here, then I want you to hover the mouse or the little arrow on top of mass A. Just put the tracker right on top of mass A, and then I want you to hold the Shift key and click your mouse. Shift, click, right on top of this. And then what's going to happen? The video will automatically go forward 1 frame. So this ball will then go over here. Then what should you do? Shift, click at this spot. Then it's going to go forward another frame. Shift, click, and so on. Do that for mass A, both before and after the collision takes place. Shift, click, shift, click, shift, click, shift, click, shift, click, until you've got all your data analyzed for object A. Then go back and repeat that process, clicking on mass B, and then shift, click, shift, click, shift, click for mass B, both before and after the collision. That makes some sense? Like I said before, you don't have to remember all of these steps. You can look it up. Okay? Honestly, I use this software program a couple of times a year. Okay? Sometimes I forget which combination of keys it is, shift click, in order to analyze each dot. Like, if it's been 6 months since I've used it, it's like, is it shift click? Is it control click? Which one is it? What do? I look at the instructions, right? You don't have to remember them all. You just have to understand them all. So what comes next? Well, you should see some data over here in the bottom right-hand corner. How well you can see this from where you are, I'm not sure, but if you click on this drop-down menu, there's a mass A and a mass B. Click on mass A. This is the time. This is your X position. And this is the Y position for mass A. What I want you to do is select it all by going Control A, then copy it, Control C, and then paste it into a Google Sheet with Control V. That's all your data for mass A. Then I want you to switch it from mass A to mass B. Control A, Control C, Control V into Google Sheets. Now all of your data is now transferred from the tracker program into Google Sheets, and now you can start plotting some graphs. All right? What do you need the graphs for? This is the template that's going to appear in Google Classroom for you already. Wherever you see some of that purplish, pinkish, fuchsia, whatever color it is, you're going to delete that. Those are just instructions. You're going to have 8 graphs here. Hey, what are those graphs going to be? Well, you need to get the X component of object 1 initial, the X component of object 2 initial, the X component of object 1 final, and so on. You're going to have 8 graphs corresponding to this, 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 and this. Each one is going to be a position time graph. So position time initial for object 1, position time initial for object 2, position time final for object 1, position time final for object 2. Please listen carefully, because I will zing you like crazy, Marks, for not doing this, okay? You need to put them in the order they're listed here. First graph, second graph, third graph, fourth graph, fifth, sixth, seventh, eighth. You're going to insert them into your document right here in that order. And I want you to display the equation so that we can see the slope or the velocity of the object in each one. Why is it important that they go in that order? It's for every lab that gets handed in here, I go through and I check the numbers so that I can tell whether, you know, if you got 38% error, to tell if you're right, if you got 38% error. And if we're dealing with 8 different velocities and everybody's got them in some kind of random order, it is a nightmare for me to go through and check it to make sure that you've got it right. If it's in the same order, I've got a system for figuring it out whether you're right or not. Okay? So make sure you put them in that order and label them so that we know for sure they're in that order. Okay? Now, once you've done that, once you've got these velocities filled in, then you're going to do a little bit of analysis here. Calculate the initial momentum for X component. That's going to be M1 V1I X component plus M2 V2I X component. Do the same thing for the final momentum. And then your percent difference. It's going to be actual minus theoretical over theoretical times 100. What do you think my actual value is going to be, my initial or final? What do you think my theoretical is going to be, initial or final? Theoretically, the final should work out to be the same as the initial, right? So my theoretical value will be my initial, and my actual value will be my final. Make sense? Final minus initial over initial. If you're within 10%, good. If you're not within 10%, explain it. Yep. Same deal for the Y component, percent difference calculation, and then your conclusion, which is, was it conserved in the X component? How do you know? Was it conserved in the Y component? How do you know? And then your sources of error plus suggestions for improvement. Remember, you're handing one of these in per group, so you can all work on it. Anything that's in purple or fuchsia or whatever color that is, delete it. It's just instructions. What do you need to hand in for this? Whatever's on that sheet, whatever's on that template. If it's not on that template, you don't need to hand it in. Now, I think that's just about it. But I do want to point out one more thing that confuses people a little bit sometimes. you only have two data tables, right? It's two big data tables. There's time, X, and Y for object one, and it includes initial and final. It's a big data table. You're going to change that data table into 4 graphs. Right? You got time, X position, Y position, which is going to turn into 4 graphs. How do you get 4 graphs from that? Well, what I'm going to suggest you do is, first of all, change that into this. Make it into 2 tables first. Make sense? So you've got a time in X, a time in Y. Now we still need 4 graphs from 2 tables. Well, you understand that this is going to be initial and final. Somewhere down here, the collision takes place. This would be initial data, this would be final data. Initial data, final data. How do you know where to split the table up? You're actually going to have to, go ahead. No, they could, but certainly not necessarily. You're going to actually have to plot a couple graphs in addition to those 8. You don't have to format them nicely. It's just going to be a couple rough graphs to see where the collision takes place. So let's say I'm plotting X position versus time, and I get a graph that looks like this. Where did the collision take place? Right here. So split the data up wherever that collision took place. Does that make sense? Create 2 graphs from that. So instead of what we have right there now, it would become this. Object 1, X component initial. Object 1, X component final. Then object 1, Y component initial. Object 1, Y component final. 4 graphs coming from 1 table. Then you're going to do object 2, the same way to get your 8 graphs. Right? A lot of work, right? A lot of work plotting graphs. Although if you're good at plotting graphs in Google Sheets, it tends to go really, really quickly, actually. But we're giving you an opportunity to split up some work here because there is some redundancy here, right? If you have to do the same thing so many times, we don't necessarily have to all do it that many times each.